Swayam Prabha. Digital India. Educated India.
Yes. So now we will do the hands-on session. We'll try with these 4 notebooks first, and then we have more time, then we can do more. But let's start with these 4 notebooks first. So like the other day, we will first go to the Jarvis website, which is jarvis.nis.gov, and there we will. Oh, I'm typing it wrong, of course. And then we will click on the tutorial section, then click on Jarvis Tools Notebooks. Okay, and then we will start with the which one is it? Day 3. Let's see, day 3. This guy. So AI1. Let's start with AI1. What is AI1? So I click on AI tutorial, machine learning scikit-learn still fatigue dataset. So this comes from this paper. There you go. It's like few years old. 2014, a group of researchers, they wanted to predict the steel fatigue based on machine learning. And the idea was just from chemical formula, chemical composition. And they want to predict, so they have descriptor like chemical composition, other some processing data like ingot size, reduction ratio, we have heat treatment conditions, and want to predict is like yield strength, ultimate tensile strength, and so on. So you can read more details about this, but as we are talking about this, we have chemical composition, which is how much percentage of carbon, how much percent of silicon in a steel, manganese, phosphorus, sulfur, nickel, chromium, copper, molybdenum, and so on, and some the processing conditions, and we can okay. So we first of all, everybody got here. Anybody has trouble getting here? Can you repeat the instruction? Yes. So yeah, we go to the jarvis.nis.gov, right? And then we click on the tutorials, and then we go to the first one, which is Jarvis Tools Notebooks, and then we click on AI tutorial. Okay, here you see AI tutorial. So AI1, which is ML and still. Yes. Okay. Anyone else having issue getting here? And remember, you have to have Gmail login and stuff. So you just, I might have to log in. Damn, forgot about this. Okay, now I'm logged in. Yes. So we will click this. Some helping library we will install. This is just for reading. This is a package to learn Excel sheet, like .xlsx file in Excel. This is a package just to learn. You need that. Okay, still connecting. Okay, pip install. So this paper that I showed to you, they have given the data for their machine learning in a supplementary information. So we're gonna download this using a command called wget. So wget is a command to download in Linux. You can see ls is a command to do list file again. You can see the file is here. And pandas is a library to load Excel file. So we're gonna load this file and see the header or the top portion of this Excel file. So here as we are talking about is NT here is normalizing temperature. HT is through hardening temperature. These are all descriptor. Remember we talked about it before. So we have all these descriptors, and the Y is fatigue. I forget the unit of this. It's like 107 cycles. Okay, so we have 27 such descriptor and 437 data points or rows. Is that right? Yes, 437 rows, 27 columns. Okay. And there are some tools you can do df.info and stuff, but doesn't matter. This is just looking at the data and everything. So remember we talked about EDA, exploratory data analysis. So in this plot, what we are doing is histogram of the target data, the fatigue, the reduction ratio and stuff. So we'll just click this. And this is way to plot. If you're not familiar with Python, there's a library called matplotlib. It's like MATLAB. So you can see fatigue is varying from this to this, reduction ratio, S and NI and stuff like this. You can plot this. There are other ways to plot it as well, like density plot, especially when you are doing some machine learning paper. What we usually do is like first figure is a schematic, where is data coming from, where is it going and stuff. Second figure usually is this kind of statistical plot, right? And just to know the limits of your prediction, where it might work, where it might not work, and so on. So here we are plotting just the chemical composition, carbon, silicon, manganese, and so on, and how much their percentage vary, right? And we also plot the heat treatment conditions here. You can see the distribution. Sometimes, before doing any machine learning, we want to calculate the correlation between the features. So if it's a heat condition, maybe it's related to cooling condition or something, or if it's density, it might be related to volume, that kind of thing. So we do, if it's like a n number of descriptor, there will be n by n plot or n by n matrix. And this is just correlation. In pandas, there is a thing called .cor. That function will automatically calculate the correlation, and you can see there are, when there is a 1, that's been highly correlated. When there is 0, there's almost no correlation. So you can see, of course, it will be correlated to itself, right? It makes sense. But there are also certain points where, for example, this dt is very much correlated to all this CT, dt, and TT, and so on. So it's like you can plot this kind of correlation. And then you can also do principal component analysis. So principal component analysis is a way to transform n degree of data to a reduced dimension of data. And do I have some explanation here? If not, you can read about this. So you can, the default is 20 principles. So here I think we have 27 something features, and we're trying to reduce into 20 dimension. So we do something called fit transform. So you'll take this data. Oh, by the way, first we have to take only the initial feature data, and we have to drop the target data. So that we have only the features data, right? So we are dropping the column which has the fatigue, because we don't want to touch that in machine learning. And then we do something called standard scaler. What is standard scaler? So this is usually machine learning models, they like data between 0 and 1 somehow, okay? If you have too much data, like 1,000 and 1 is 0.000001, then the models have very tough time to make a model, right? So this standard scaler is usually a good practice. Just give your data, and what it will do is it will do 0 mean and unit variance, convert it in a way that all the rows, it will calculate the mean and standard deviation, and it will take the data and remove the mean, and that will be for numerical stability and stuff. And suppose you have a new prediction, and you can get the scale variable and then give it to something like principal component analysis. So when I say parenthesis, it comes with a lot of default parameters. And you can see Google Colab will show you, if you just put your cursor here. Yes, it can show you the hyperparameters there. For example, here we have oversamples and so on, PCF components, none, which is basically everything. Yeah, none is basically all of that. Yeah. Oh, bigger? Yes, sorry. Yeah. All right, so that's right. So we can have a 20 principal component or n number of principal component, and we can get something called explained variance ratio. So it's basically a way to see where does it saturate after how many points. So if you have 25 or 27 features and if it starts saturating around 10, then that's how much you need. You need only 10 PCA components to do machine learning, and it will drastically improve the uh, performance, not performance, but the computational cost of your model training. That's why it's very important. So we have some. We did this. Yeah, I think we did this one. Yeah, so we loaded the data, we did the standard scaler, we do a PCA, and we just plot here to see where does it saturate, and it saturate around 15 or something like this. We can also plot this new dimension from one to other. So I'm plotting here the first component and the second component, and just to see whether there are some relation or not. Sometimes hard to explain this kind of data when you have transformed into different basis in a way. So now what we will do is we'll compare linear regression, random forest, gradient boosting machine, and multi-layer perceptron to establish the relationship between the feature and the fatigue and see which one is better. So like the previous case, we will do a data split. So we loaded the model here. We have test size of 0.2, which is 20%. And then we use this function called train test split. And remember, we use this state called random state 42. So if you don't specify random state, then every time you use this function, there will be different split. This is very important to have fixed. And 42, there's a very funny story about 42. If you Google 42 Wikipedia, there's a Wikipedia on 42. This is called, what's the name? Hidden Secret of Universe of 42, the number. And it's from a movie called, no, it's from a book, Hitchhiker Galaxy or Hitchhiker Guide to Galaxy or something like this. Very interesting book. But the 42 is very much used in almost all machine learning models as a seed number. This is called seed number. Okay, so now we'll import a function called linear regression. So this is coming from the scikit-learn model with some default parameters. So if I just again hover the my cursor, then it can show you some of the parameter, which is, I mean, it's a linear regression, so not too many hyperparameters. So here, most importantly, you will see we do something called lm.fit. So any scikit-learn model has something called .fit and .predict. What do they do? So we initialize the model. This is a Python class. Remember, we talked about the Python class as a template kind of thing. So it has a function called .fit. So I can take it out here just to make you explain, because this part is crucial to understand. So we took the train data. We do not touch the test data here. So you have the x and y, and then after the model is trained, all the weights are optimized in a way. Then we do .predict on the test data, test input data, and then we calculate the error. We know the ground truth. The ground truth is the y test. So y test is the ground truth. Prediction is the prediction from the model. And then we are using this metric called mean absolute error and R2 square to see how much is the error is. And we also do a plot. So any machine learning, you will see a lot of scatter plot like this. And if it's on the x equals to y line and this line, as close to this, then you have better model usually. So did we click on this? There is a linear regression model. Let's see. So we get the mean absolute error of 24. I should have calculated the baseline model too, but maybe I missed it. Maybe that will be your homework. Let me add here. Homework, calculate baseline. All right, so we did this for linear regression 24. So R square usually go from 0 to 1. So here is 0.97, which is not bad. So now we are going to do random forest model. So usually people say that if your best model is something, your second best model is always random forest. It's like a joke kind of thing. So random forest always works for some reason. for some peculiar reason. And it's based on decision trees. So random forest, again, dot fit, dot predict, and we can plot it and see here is 19 versus, what was the previous number? 24. So we can see some improvement here. And you can see it's more looking on the x equals to y line. And then we can do something called feature importance plot. So you have these 27 features, and it did remember this, we did this if and else statement. So when we do this training, the model also remembers what is the path it took, which path was more important. And based on this, you can do something called feature importance plot and see which feature was most important. So this apparently this NT and DTCR features were most important, right? And the least important was this DB or something DC, right? So it's important to understand this. Some of these will not be captured by your correlation plot, because those correlation things work in linear regime, and these are somewhat non-linear. So another method is gradient boosting. So now we are going to use gradient boosting decision trees, which is my favorite method. If neural network is first, my second favorite is gradient boosting decision trees. So it's 15 versus random forest is 19. So sometimes the feature importance from the gradient boosting is different from that of random forest. So it's still all the T stuff, but still there are some good correlation between the feature importance of this and this. So if both of them are kind of agree, then you have some confidence, yes, maybe these features are indeed important.
Can we get feature importance for linear regression?
Yeah, weights, that's all it is. You just have the y equals to mx plus t c, right? So m higher is basically more important. Yeah. So congratulations, you did your first machine learning notebook. Yeah. So I want to see how many. Sometimes what we do, I did not do here. So first you will do PCA and then do first standard scalar, then PCA, and then do dot fit, dot predict. Sometimes the models get better because you have less things to worry about. Yeah. So these things are called pipelines, scikit-learn pipeline. So here we can combine multiple things, such as standard scalar and the support vector machine, and then becomes a new type of model. You can have standard scalar, max min scalar, PCA, kernel PCA, this, that. Again, what it should do is lower the error. If it doesn't lower error, there's no point doing all of that. But you can have this pipeline, and instead of model.fit and model.predict, you will do pipe.fit and pipe.predict. Okay? So you can have a PCA here as well. So again, please disconnect and delete runtime to save your time once you are done with this. Now we move on to the second notebook, if you allow me, unless you have any questions. No questions, right? What is this? AI2. So let's see. I don't remember what it is. It's been a while. So let's go there. Oh, this is using the this is comparing different type of features. So in the previous notebook, we compared different type of models, gradient boosting, this, that. Here we'll compare different type of featureizations. And here we'll be using a package called LightGBM. So a gradient boosting machine. There are different type of gradient boosting regression, XGBoost, LightGBM, CAT boost and stuff. So we're going to use LightGBM in this example. So yeah, we are just installing software, importing libraries here, and then to get the data, right, we are getting from GitHub somewhere on, we are getting the data on formation energy. Okay, so let's see how it looks like. Yeah, so you can see the top 10 entries. We have composition like this. It's just chemical formula and the formation energy. And the idea is I want to make a model that I can give arbitrary composition and predict me formation energy, right? Actually, this is the first time, this is like 2016 or 17, when I saw this, I was like mind blown, literally. How could it possibly do that, you know? We have to do experiment, we have to DFT, and these people get just to dot fit and dot predict and predict energy. So it was really quite interesting. Okay, so we have, we have loaded into pandas data frame, and then collect the chemical formula descriptor composition based only, yes, and try modifying. Okay, so here we'll have 3 descriptors. So remember CFID, although it has RDF and DDF and all those kind of things, we'll only take the chemical formula part. So that is the XCFID, XMACPI descriptor, and element fraction descriptor. So in Jarvis tools, it's already kind of coded up. So if you give a formula, it already give you a descriptor. So if you want to test it out, let's test one of them. Let me see if it works. So if I put here like this and put chemical formula like, I don't know, Al2CO germanium 5, I don't know what I'm typing, but let's print this. So you see this, it gave me 2 things, A comma B. What is A comma B? So A is the name of the descriptor. Oh no, A is the value of the descriptor and B is the name of the descriptor. Yeah, so like mean MACPI, whatever, GS magmom, volume per atom, melting point, all these kind of things. So what it did is, it had aluminum melting point, cobalt melting point, germanium melting point, just took the average of that. Okay, that's one descriptor. So you can change it from MACPI, I think, to some other source too. But in this particular example, we did MACPI, and then we are calculating the descriptor and the feature names, and the value is the target data. Okay, so I0 basically mean here the first X. Let me take this out. So I0 is basically the zeroth value, and 1 is the first value, okay, of that matrix. So we got that 0 and 1. We calculate that descriptor and add in an array called xmag pi, and y is our target data, and we also store the IDs. And then we make a numpy array. It's a very common way to convert into numpy. And then we calculate the baseline, mean absolute deviation here. So here the baseline is 0.07. So 0.7. So if your model has mean absolute error less than 0.7, then don't do machine learning. Okay. So yeah, all right. So these are some of the names we already printed. So now we're going to set a train test split, and we put the test size of 90-10, and then we have a random forest regressor. We do dot fit, dot predict, and we calculate root mean square and mean absolute errors. So we got MAE of 0.25, while the baseline was 0.7. So it's better. How much time better? 2.87 times better. Usually, machine learning models have MAD to MAE ratio of more than 2 to 5 and stuff. If you can get more than 5, then really amazing model. If you get up to 50, Nobel Prize. Just kidding. But yeah, so it's around 3 or more than 3 is what we need for this kind of models. So here we are plotting the test data and the predicted data. I don't know what happened here. Oh, I did not run this. Sorry. By the way, in this year we had 2 Nobel Prize for machine learning. Do you know that, right? Yeah. Now we refine a random forest model using hyperparameter search. Yeah. So here in random forest, there are several hyperparameters, like how many number of trees, when you make the trees, how much the depth of the trees and stuff. So we're gonna vary the number of trees, also known as estimators, 2 trees, 3 trees, 4 trees, 5 trees, and the depth of the tree. So 2 tree, 2 depth, 2 3, 3 depth, and so on. And this is called hyperparameter tuning. And we give to something called grid search cross validation. What is grid search cross validation? So it will make the grid of all the possible combinations. So 2 2 2 3 2 5 blah blah blah, you know, all the grid, and then it tests out all the models, and it will see which one is the best model, and then it will give you the best hyperparameter. This is called grid search. Sometimes there is something called randomized search CV, which can automatically search in a more sophisticated way, and then give you more efficient way of getting hyperparameters rather than just, you know, brute force testing everything. Okay, so we did this one already. Feel like no, we did not do this one. So for each of them, I think it will print for each cross validation what's the score, and it will give you the best regressor for after the grid search. So when you do grid search, it comes with the best regressor model, which is whatever that variable dot best estimator. So best estimator is basically your best model. I don't know how long does it take. I don't know. But let it do its stuff. But it will train the oh yeah, because it's doing a lot of hyperparameter search, right? So it's taking some time. It will look like this: x equals to y line. So it's DFT formation energy or experimental formation energy and random forest or machine learning formation energy. So now we will see the feature importance, which is the most feature importance. Apparently, so we can take the average of the melting point of each constituent elements, or minimum or maximum. So here it seems like the minimum of the melting point of the constituent element is the most important feature. Of course, we did not know it unless we did the machine learning. And other than that, the space group is like, this is really high. I don't know why it is so important. Like 4 to 3 times higher. Okay, so training is done. We plot this data. And we are looking at the best regressor feature importances. And we're plotting only 10 feature importances. Is that it? Oh, okay. So this was an example of, oh, I see why. So we did random forest and which one? Linear regression, right? 2. So what we, say it again? Oh, okay. It's only with the MACPy, right? Oh, I remember now why. What's what I'm doing. So I was supposed to give you as homework with some other things, like try it with element fraction. So this chemical descriptors. Let me try to remember. It's been a while. Jarvis tools. So if I go to Jarvis AI descriptors, it will be what? Elemental descriptors. So this element fraction, where did I import from? Let's see. I don't remember anything. So we got it from stop, of course. Yeah. So here we have source can be CFID, or it can be, well, source is that, and you can also have mean only, max only, minimum only, and so on, and you can try which feature is the best, especially for chemical descriptors. How did we get the MACPy features? Oh, actually it comes from the CFID, that's why. So we can try here, instead of CFID we can get elemental features, okay? So instead of, I think this notebook, instead of calling dot chemical descriptor, which is this, what we can do is call it X element fraction or something. So look at this, how the Colab does it for you. It gives you suggestion of all the notebook and stuff. So we have to import a library. Again, I don't know how much time we have, but let's try this. From Jarvis AI descriptors import the second one, get element fraction. I think that's what we want. And then we have it here. Yeah, I think that's what we need. So let's see if that works. Okay, so it did work. So we have a new feature called XELFF, which is the element fraction. And what we're gonna do is, instead of giving the Xmag as this, we'll just give this to be XELFF, just for fun. And then we'll try and train the model. So right now it is what? We can just keep this one here. Try it here. Let's see what it gives. So 0.435 versus 0.350. So it seems like the CFID based chemical descriptor, 0.253, and here it is 0.331. Yes. So only the element fraction was not a good model. It's having more like Mac5 features and stuff was better. So you can do some comparisons like this. So in addition, I mean, these two are most popular, element fraction, and you can specify also what's the maximum number of elements and stuff. So this was the second notebook. Let me cancel this before I forget. So now we have a machine learning descriptor with CFID. All right, so what was the next one? CFID, no, AI3. Let's go there. Yes, please.
When we are using the cross validation, so basically it's calculating the best model which is giving the best average error or best splits.
Mm-hmm.
So after that particular this hyperparameters are determined,
Mm-hmm.
do we need to train the model on the full training?
No, it's already trained. Yeah, because it did for each, during the hyperparameter search, it did train it, right? Train and test. So it does reserve that information. It does store that information. So you don't have to train it again.
So during the split part, the best model also has seen all the parts of the training data.
Yes. Yep. Yeah. So is your question about data leakage?
Actually, I just want to make sure like the validation is kept, like we are taking one test and three.
Yeah, during cross validation, on the training data itself, it will do something like five-fold. Five-fold is
One part like
4-part, 1-part and stuff. It will split it and do it 5 times, right? And see which one is the best model. Give you that best model. It's called dot best estimator. The scikit-learn is, that's why it's very popular, because it has all these functions already built in it, right? Okay, so the next, okay, sorry. Any other questions? Where have you worked on uncertainty before? Do you guys remember anything about uncertainty? Quantum mechanics, Heisenberg, yeah. What's the uncertainty there? What's the value there? Rotational momentum, right? Yeah. So I mean, they say that your model should have uncertainty, but as low as possible. There should always be uncertainty. Okay, there is nothing certain in this universe. That's the idea. But as lower is better. Yeah. Anyways. So next one is this CFID descriptors, but again, we don't have to do this. There are other descriptors too, like Beller, Prenalo and stuff. This is just an example. So we first install it, like previous examples. And so in the first day, remember for a silicon, we got the CFID descriptors. I don't know if you guys remember. Like from Jarvis, you give the atomic structure and you give the CFID descriptor. So in this example, we have calculated the CFIT descriptor for 80,000 materials or 60,000 materials automatically. So you don't have to do it like manually. Okay, and we have stored this in a format like called CFID3D. So when we run this code, it goes to the fixture, downloads the data, unzips it, loads it in this format automatically. So all the features will be here. This is for 35,000 material. I'm sorry, that's 36,000. So you see, it's right now downloading the CFIT descriptors. And these are some of the properties in the data set. But like formation energy, band gap, meta-GGA band gap, bulk modulus, shear modulus. Epsilon is basically your dielectric constant. M-EPS is basically your meta-GGA dielectric constant. Seebeck coefficient, power factor, N-type and P-type. SLM is solar cell efficiency. Spillage is topological spillage. So if you are familiar with topological materials, you know there are, while it's downloading this, they are metal, based on band gap, there are metals, semiconductors and insulators. But there are certain materials where metals and semiconductors can exist in same phase. And some surface will behave metallic and the other surface will behave as insulator. And that can have an application in quantum computer and stuff like this. But we did not know how to characterize this. How do you know whether a material is topological or not? So we had an idea that we calculate the wave function with and without spin orbit coupling and compare the wave function. And if it's different, then it should be topological. So that how much extra electron you have due to spin orbit coupling, that is called spillage here. So we have that data, dielectric constant, piezoelectric constant, effective mass, and so on. Too many properties. So what we're going to do here is we will convert this into pandas data frame. And so yeah, anytime you develop your data set, I would recommend make it in a format that can do a pandas data frame. It will be good for you, good for everyone in the universe. So df.columns, we have this many columns. And then here we'll be loading only formation energy. So we'll take the desk, which is a descriptor, the 1557 descriptor, and the property, and make sure this is like 1500 descriptors and there's no some crazy number, and add x and y, just your input and output. And what did we do here? Okay, so then again 90-10 split of the data. Oh, sorry, this should be this. It will give error. So we got the formation energy, we can do bulk modulus. So I may give you an exercise for bulk modulus here. So, and then here we'll take only 500 data points just because to save some time. So we have training x1, y1, testing x2, y2. We can always do hyperparameter, but here we are giving you some hyperparameter which we already found. And then we train the model using dot fit. So we have the gradient boosting decision tree model, and we do the dot fit and the dot predict. Then we can have something like mean absolute error, R2 square. We are talking about. Yes. How many? So for gradient decision trees, I think you have these 3 or 4 main. So like number of estimators, learning rate, and num leaves. These are most important for this model at least. Yeah. So you do the hyperparameter search that we did in the previous example. Give a grid and just let it search for this. Here we have 3: n estimator, learning curve, and num leaves. And you give her like 100, 200, 300 for num leaves. Num estimators, so on. All right, so we have dot fit, dot predict, and then we'll plot this, our favorite scatter plot. So you can see it's not that great, but it's decent size. Again, we have not trained on all the data set. We had only 500 sample points. See, so we got 0.339 mean absolute error for formation energy, which is not that great, but again, since as an exercise, instead of gradient boosting, you can try random forest or linear regression and compare the performance. So this is an example of how we can use pre-made fingerprints. Sometimes computing fingerprints can be time consuming too. So you can just submit, go to sleep, or go have a coffee, not coffee, you take a break, go on a vacation, and just let it compute all the descriptors. And then come back and train your model. The good thing is once it's computed, you can do a lot of hyperparameter search, you can do a lot of analysis, but having the descriptor is useful. So because some of the materials are very crazy, like metal organic framework and stuff, these descriptors are very, very slow to compute. And then that's why graph neural network becomes more popular, like deep learning model and stuff. These are much faster. So we started 9:30, so end at 12:30. Okay. Yes.
But the paradigm plots which we are able to, like, which we are able to see,
Yes.
they kind of, like, these ML models are not too performing well, right?
No, this is not. Yeah, this is not good.
Yes.
This is just
So we can't deploy this in reality.
I mean, we can, but use at your own risk, kind of thing. I mean, see, we had only done 500 data points. I think if you had more and more data point, which is like 30,000, it will be a much better model. I think the order will be like at least 3 times better, 3 to 4 times. Yeah, so this will be an exercise that you guys can do if you are doing this for a credit course. And now the last one is, unless you have any question. Do you guys have any questions so far? Do you guys? Yes, go ahead. Number of columns multiplied by the number of samples will be total number of data. Okay. Mm-hmm. Yes. Okay. You mean the training data points? Okay. Mm-hmm. Oh, you mean like do PCA and stuff? Yeah, you can do that. And one thing I did not talk about this. We talked about the dimensionality reduction, right? But we also should do something called learning curve. Okay, so what it is? So it's very important. So suppose you have 1,000 data points, you'll train a model for 100. So this is the number of samples, and this is the error. It should go like this, and you'll see that it saturates around and here. So this is the kind of ample amount of data. That is what you need. So yes, it is the error and the number of data points are indeed correlated. So best feature and best amount of data that we have, then it's like golden, right? This happens only for energy models. I've seen that, like formation energy and stuff, not for other properties. Like band gap is terrible. So I saw a paper by a group in Germany called Alexandria database. So they made a database for 5 million materials, and they showed that the band gap is a very difficult model. The error is like 0.2 EV, which is very high, and they made it 0.05 EV or something. It's really good. So I started thinking, why is this, right? How did they do this? So they made this learning curve. So it goes fine until 10,000 point, and after this there is a huge drop. So what happened? So they didn't write this. So my speculation is they started making more metals in the data set. So if everything is more zeros, your mean absolute error will go 0 and 0 and 0. So sometimes, again, this is just a speculation. So don't quote me on this. It is being recorded, right? Okay, never mind. So this is just a speculation. So sometimes when you generate data set, and these kind of things can guide you, but don't completely rely on this. Think of why is it happening too, right? So because it's a perfect example, like if you have more data around 0 and your prediction is also around 0, then your error will be close to 0, right? So I think that's what happened. So even in this case, learning curve is important, feature importance is important, and so on. Yeah. Anyways, we have like 7 minutes. So all right, so we did this, and the next one is CPU versus GPU, which is just next to this, which is 5th example. So here we'll be installing light GBM with some GPU features. So anytime you use GPU, how many of you have used GPU before? You guys are rich. Consider yourself rich. So anytime you use GPU, you can use this command called NVIDIA SMI. Okay, so this will give you a state like what is the power, how much memory is being used, how much volatile memory is there and stuff, what kind of CUDA version is there. So that can also help you guide what kind of model to use and what kind of driver to use, what kind of software package to use, and so on. So again, while installing, there's a big joke in our group that the future money is not gold, is not crypto, is GPU. People who have more GPU are considered like wealthier. NVIDIA has plenty, yes. All right, so NVIDIA SMI in this case gives us this result. You have only one GPU, you have how many memory? This many megabyte of memory. Right now we are not using anything, so it's 0% of uses. 70 watt. So some of these GPU training costs a lot of heat, right? And they say that if AI model doesn't come with Terminator and stuff, definitely the global warming will kill the Earth. So there are a lot of infrastructure how to minimize the heat cost of this as well. Anyways, so same thing. I'll just go through this. You can run it on your own. But my goal here to show here in this example is if you train using device equals to GPU and versus device equals to CPU, same hyperparameters, you get time difference, right? So we get the time of 126 seconds, and in the second one using CPU, we get 135 seconds. Okay, so it's not noticeable, that much noticeable, but definitely improvement with GPUs. And if you have more and more data, then you can get slightly better performance as well. Sometimes it's not always linear, like just because of GPU you have really high performance, it's not true. Okay, so you have to always do something like scaling analysis. The scaling analysis is also very important, as if you are really a material informatics person, you have to submit proposals for money or grant, then you have to show some this kind of scaling behavior. How does your code perform? So this kind of analysis is very important. Did we run this one? Yes. Same stuff here, just downloading the data. So it's not too much brainer, but okay, this thing is important. This is called magic functions. How many of you know magic functions? Please raise your hand. One. Okay, it's just in Jupyter notebooks and stuff. If you see this percentage, it means something special. What does it mean? So if you are plotting something, one of the common is percentage matplotlib in line. It probably suggest me. So it will plot data on the spot here. It will display as a HTML. Percentage capture is sometimes it produces too much output. I just want to not print it. So you can put percentage capture and stuff like this. So yeah, here the idea was using GPU in terms of enhancement of the computational time, but some cases when you have a lot of data, or sometimes even for small data, you can get error because of GPU processing. Okay, So always be mindful of that as well, because the architecture of it and stuff. So there's not. Do you guys mean to complete this, or just you guys get the point here? You guys get the point, right? Yeah. So okay, we did this already. So what I can suggest is, so I'll show you a model deployment, model deployed. So one of the web apps is, let me see if I have something here. This is a CFeed model. It's been a while, but let's see if it works. I think this one works for sure. Yes,
If you don't mind,
please.
a question regarding the previous notebook.
Yes.
So, like, I was just seeing the source, and like in the seventh cell, I think.
Is it this one? Yes. 7th cell. Please tell me, this one or
Yeah, the third one was there.
third is this one?
So why did we consider a weird learning bit? Like, why not?
Okay, sorry. So I had done some, our team has done some hyperparameter tuning already, and they're just using that as fixed.
So how did you obtain that?
Oh yeah, so we had like learning rate from point 0.1 to 0.3 as continuous variable, and then it find me this variable.
So ideally, like from what I'm familiar.
What range, right?
Yeah. So we use something like a for loop and then print out everything and then capture the system, right? Like let's say 1 to like 1 to 50. I think like 1, 2, 3. All these things maybe I can iteratively
Yep.
find out.
Mhm.
But like, did you use any inbuilt program?
Yeah. This the randomized search CV is it is especially if it's a float number, it will do this kind of thing automatically. Search it, not like this float, right? How many precision you can take, so it can identify itself. Yeah. Good point. Yes. Scaling analysis for GPUs. Oh, scaling is like more number of data. How does it scale? Or more number of processors. Yes. So, or if you have more and more GPU, does my time reduce in a linear way or not? Sometimes just having more GPU does not mean it just decrease the time. It just saturates some time. So that's why scaling analysis is important. So if your GPU saturate after 4 GPU and after that it doesn't really improve, then your grant manager will not give you more GPUs. There's no point. You're wasting the resources. That's why. Yeah. So again, let's deal with questions more. If you have more questions, but this is a deployed model. Okay, I'm gonna have to sign up and stuff. I don't want to do this. Oh, interesting. So let's see if it works. One of them. Cross fingers. No, it doesn't. How about this guy here? This is for a graph neural network model, but we can do this. So yeah, it took this atomic structure, convert into a graph, input to a trained model already, and predict you on the spot. So this is how you deploy the model in a way. And believe me or not, a lot of people who do not have too much compute power, they are just doing this and doing some sort of papers based on this. It's a level of that. So you do a lot of screening based on this, find some material, and then do DFT on it, publish paper. So that's the advantage of this kind of model as well.
So
What
you
is this
hosted in
one?
some local server then?
Yeah, it's a VM. This is for, I think, carbon capture. Yeah, so I think it will predict the, or maybe not. Maybe what happened, I don't know. So there are some models for predicting like battery material, catalyst material. So anytime we do a paper in our group, it's kind of painful, but I still ask them to publish the paper, but give the data in the Figshare, give the code in GitHub, give the benchmark, the comparing with experiment and everything in something called leaderboard, and make an app and make it available there so that people can actually use it. That's actual output. Although they hate me for this, but this is a good output. Yeah. Yeah. So we saw the scaling behavior, right? So we talk about the number of GPU plot. We talk about the power as well, right? Power, um, time per epoch, time for inference. Inference means like prediction timing and stuff. Like if you want to have prediction on T4 GPU versus V100 GPU versus P100 GPU versus H100 GPU, A100 GPU, which one is faster? You'll say, oh, mine is A100 is so much faster. I'm going to use this. So that also helps. So yeah, these kind of things, more and more testing helps. I don't know what's the state of the art. H100 is also old now. I think there's some new stuff. Yeah, some more. Yeah. Any other question? How to know whether should I use CPU versus GPU? If I believe one of the rule of thumb, it would be if you are using some neural network based model, take GPU. Yeah. Honestly, yeah. Better to have both. Yes. I mean, VASP has some machine learning thing, right? Force field. They started using machine learning force field using Beller-Penalo, I think. I forget which one is this. MTP or Beller-Penalo? I forget which one is this. Beller-Penalo, yeah. So they have this in the same framework, but I don't know how efficient it is and stuff. So especially because a lot of people are making this universal potential and everything, there's no point of fitting if it works for your system. If it doesn't work, then you have to do it. But if it works with this universal potential, then yeah, just use that. I see. I feel like architecture is saturated. It's just data game now, more and more data. So it's very hard, especially when you write a paper on architecture, you have to beat some of these models. Very hard to beat. Because the model has learned a lot already. So it's very hard to beat such models. It's the same data set, no further data set, same data set. So I have seen some papers being published based on inference time. So my model has faster inference time, so there's a paper. Especially in computer science journal and stuff, this happens.
What do you mean by inference time?
Yeah, so like how much time does it take to predict something? Some model take 3 seconds. The new model takes 1.3 seconds. So a paper. More about that? Yeah. So yeah, I mean basically the error, right? So the error is a function of multiple features, right? And some feature affecting more than others. So loss being contributed from one feature versus other feature disproportionately. So if you want to have equal stand, we should vary the weight of those way in a way that individual weights are comparable, individual losses are comparable. So that's what I mean. Like you have to sometime go there and manually put the numbers of loss function, especially for neural network and stuff, not for scikit-learn stuff. Scikit-learn is like a lot of them are automated, but especially for those functions like energy versus force versus magnetic moment and stuff, you have to give some different importance. And other than that, you have to have different learning rate. So for example, you have a cost function, but if you're varying the parameter too fast, right, then you might miss some points. You will be jumping around too many local minima rather than looking at a minima and going to the bottom of this. So in the loss function also you have to specify your learning rate. So like in neural network, very common is 0.001 is a very common neural network learning rate. But if you are doing fine tuning of the model, like if you have a model already trained, you just want to have some new data points, don't vary too much, then put a learning rate of 0.000005. Just slowly vary it. See, so that's what you do. What you're doing is guiding the loss functions in a way that my overall model doesn't change too much, right? So those kind of things, learning rate, batch size also similarly. So yeah, so think about the things that loss function depend on. Yeah, same with the GPT. Huh? Which one? Gradient. Gradient. Vanishing gradient is important. Double descent is important. So I didn't talk about this, but based on the optimizer you use, you might run into problem where um, it's like this. If I remember correctly, if you plot, if you are doing neural network, if you have an epochs, epochs is basically how many iterations of data you have passed through in your model. It will go like this, and suddenly like this, and like this. So what happens suddenly at some point is your the gradient of the loss is changing too much sometime, right? Or becomes zero. When its gradient becomes zero, then it becomes numerically unstable, right? Obviously, and then you don't have a good parameter set. So that's one example. However, there's another thing I want to talk about. Yeah, double descent. So double descent is also a very good concept in machine learning. Sometimes your model is going down, down, down here, right? The loss is going down, and it goes like this, and you thought, okay, this is my optimum epochs. But according to double descent, what happens? If you turn little bit more enough, it will go further like this. This is called double descent. So sometimes what people do is just set a maximum number of epochs and let it run. Okay, so this is called double descent. What else?
Is the double descent issue because of the multi-node nature of the object loss function?
Multi-level nature, right? I don't remember what is the reason for this. It's just scene behavior. Maybe it's in the paper, but I don't remember what's the explicit reason for this. Yeah, it's like for many neural networks this happens. Why it happens, I don't think it's well understood. Right. Yeah. So there are many optimizer and stuff like this, but some of them are pretty standard nowadays, and people have done a lot of benchmarking on established data sets. So one of the most common is called ADAM-W. ADAM-W. This is very popular now for most of the neural networks training. Most of them use this one just because it's stable. Yeah. Oh, so the scikit-learn based. Should be. So those are like classical algorithms, like LBFGS. What else? Fire is also an algorithm. So those things are already, I think there are possibilities. So BFGS, LBFGS, quasi-Newton, and few more are there. I forget. But you do have some flexibility, but this one is most popular, LBFGS. So when you did dot predict, that's what it did, LBFGS. Yeah, by default. These are for scientists, BFGS. Say it again. Scikit mode pipeline. Yeah. So yeah, sometimes we think of, oh, maybe we should do standard scalar first and then PCA first, and what's the best combination of this, right? So instead of doing this, consider a for loop where it goes over all of that, makes pipeline, does testing, and gives you the best model. That's why the pipelines are so popular. And there is a package called, especially for feature-based model, AutoML. Is it this one? I forget. 7,000 stars. Maybe it's this one. So it's for classification, it seems like. Maybe it's not the one I'm looking at. Awesome AutoML. I didn't know that exists. But yeah, there are some models like AutoML which has this kind of pipeline kind of set already for you. PyCrate? I don't remember. There's one more called Teapot. Is it? Teapot machine learning, not other teapot. Yes, this is what I was talking about. Teapot, a Python automated machine learning tool that optimizes machine learning pipelines using genetic programming. So, so you take the raw data, data cleaning, feature extraction, model selection, optimizer. It can take like PCA, polynomial feature extraction, all these kind of things automatically. So you just give it to the teapot classifier or teapot regressor, and tell it like how many generation you want and how many times you want to test it out and stuff. Those are the variables, and then it will do all possible. So teapot has these pipelines like polynomial feature, random forest classifier and stuff. It has a list of all the hyperparameters to tune. Let me see if I can find it. Config, yes. Maybe this one. Yeah, you see this is all the hyperparameters you search for. It is already coded there. What should be the range of those values? And it just goes over all of that automatically. Teapot. And there are a few others too, I think, but these are some of the examples. So tomorrow will be deep learning. Have you guys trained deep learning before? Deep learning model before? 1, 2, 3, 4. 4 only. So tomorrow will be too much stuff to take, but those are the models which are really deployed in public uses and stuff. Thank you for your time.